12.1 Electrons and Atoms, HL Chemistry for the Atomic Project Theory. Let's start. First is the ionization energy. The first ionization energy is the energy required to remove 1 mole of electrons from 1 mole of atoms in a gaseous element. So this word right here is really important. You might lose a mark if it comes to an exam and you define the word first ionization energy and you didn't include this word. It's really crucial. And you know what happens when an atom loses an electron? It becomes a positive ion. So let's say we pick vanadium for our element for this project. So it becomes vanadium plus, or vanadium 2 plus, loses 2 electrons, or vanadium 3 plus. Essentially it's the same. Now, the emission spectrum. When electrons are excited, interesting word right here, you have to remember, they move to a different shell, or you can call it energy level, and it releases photon. Photon is light, and different element emits different light. You have to be aware. For example, oxygen emits green, and nitrogen emits blue, and yeah. So when it releases photon, it goes back to the original shell. So let's say it's on the second shell, it goes back to the first. I'll show you an example, but first, the shorter the wavelength, the higher the energy. Just like the wavelength diagram, you have like this gradually just changing to a long wavelength. And right here is the gamma rays, UV light, and the visible, and then the infrared, and so on and so forth. Moving on, this is the the emission spectrum for vanadium. As you can see, the lines converge right here, and then you can see lights emitted by vanadium according to how much energy is put in. On the diagram right here that I found, this is it's the same concept for every element or atom, but this is just the this right here is just the hydrogen lights that are emitted. So as you can see, the diagram on the right, or the lines and colors that you, so the longer the arrows, so right here, the higher the energy. So that when it travels far, means there's a lot more energy that will put onto that passes through the electrons. Sorry for the notification. And then, as you can see, from one shell, that the energy level of 6, the 6th shell goes back down to 2, and then from the 5th shell it goes back to 2, and the energy has a variation of energy right down here. So on the left diagram, this is where it gets interesting. You can see that as you go outwards, the shells are actually getting really close together, and then as soon as it continues on until shell 9 or 10 or 11, but you can't see them, and then until they reach infinity. So this is what you call the limit of convergence right here. You can't see them, but they're really close together, and you would have to zoom in to look at the difference between them. And when an energy is passed through an electron, let's say the electron is right here. Actually, no. Let's say the electron is right here, and energy is passed through. And the electron would travel to the limit of convergence. It will not come back. Usually it will come back. For example, it will go from here and then to here, and then when it comes back down again, it releases a photon. Now when it releases photon, you can see light and it becomes excited. But if it reaches the limit of convergence, it will never come back down. It will just fly off as a one single electron to combine with another ion, and this is what you call the first ionization energy beyond this limit of convergence, and this will make this whole atom an ion, positive ion. So there's that. All right. Next thing I want to talk about is the trends in first ionization energy across periods. So what I need to show you is the existence of sublevel and energy levels in atoms. So I've got this diagram, energy for period 4, because we picked vanadium right here, 23 protons, 23 electrons. What you'll notice is that this diagram is actually gradually increasing, obviously, because but it's important to notice that there are some inconsistencies, I would call them. There are drops. First drop, second drop, third drop. And then I have another example. This is the ionization energy for period 3. There's also a first drop, second drop, third drop. This one is just the same as this one, so it occurs every time. Now, why might this happen, you may ask? This is because, firstly, inconsistency that I talked about, so it's not consistent. Firstly, it's the shells. Now, when you have one electron in one shell, it takes less energy to remove that electron away compared to a shell that, let me draw something. So let's say I have one electron there, 2, and right there. So the change in energy in the shells, so the energy levels, the shells, this part right here, the drop in, because there's only one electron in the furthest shell, the outer shell, and it takes less energy to remove it because it's only one right there, and it's far from the nucleus, so it's kind of it's easier to pull that away rather than to pull one of these in a full shell full of electrons. Sorry for that notification. So that's the first one. Now going back to this, here's the second one. Let me just write this one as the shell. The second drop, so the second drop right here, is because of the sublevel P to S. I have a diagram right here, gradually increasing, but exceptions. Sorry, not that one. Right here. There. So the change in sublevel from P to S. As you can see, there's only one electron in P. P can hold 6. I'll get back into that later on in this video. So it holds only one, and it's easier to remove that electron away because it's gonna leave it with a much stronger, I would say, a much stronger force to hold the electrons. So it leaves it with this, and then it's harder to pull this one off, because it has another electron there. So it's easier on this one, because it's by itself, so nothing's disturbing it. And then also on this, I'll talk about this one later on. And also, so yeah, that's because of the change in sublevels. The third drop, as you can see right here, third drop, also the third drop, is because of the mutual repulsion. Now this may be a new word for you, and mutual repulsion is basically on the Hund's rule. You have to fit. Let's take the P sublevel. You would have 3 boxes, 3 spaces, because sorry for the notification. It can only hold 6, and then to fill up is you fill the boxes like this with electrons. So full will be 6 like that, but sorry. And as you can see on the fourth one, so on sulfur, on the drop right here, it has 4 electrons, right? So this is you have 6, and then you fill 3, that's half full. So when electrons are paired, it creates an extra mutual repulsion. So it wants this to go away because it wants to stay on the half full sublevel. Now, that results in less energy being required to remove the electron. So hence why 1060 kilojoules more dropped to 1000 because of the mutual repulsion. So these are let me draw it again for you. So this one after. This is the Hund's rule. You have to fill it one by one. So yeah, this is a result of mutual repulsion. Let's just write it here. Forgot to write it. Change from P to S. Sorry. So P to S. And this one is repulsion. Now, next thing I'm going to talk about is the trends in first ionization energy in groups. So you're familiar with groups. There's group 1, there's group 2, 3, 4, 5, until 8 noble gases. Right there. Right. So as you go down the group, atoms have, as you go down the groups, like down there, as you go down, you would have more protons, and you know that protons equals to number of electrons, therefore more electrons, hence more shells to fit the electrons. It has the same amount of electrons in the last outer shell according to the group number. So you would know this is a diagram of the first group metals in the first group, elements in the first group, sorry, and you would have, you know, the first group, one electron, one every time until as you go down along. So if you go in the second group, you have 2 electrons, and then 4, 8, and so on and so forth. And the further the electrons from the nucleus, the less the attraction. This is because of shielding effect. As you can see from this diagram, the 2 electrons is making a shielding effect towards this. So what shielding effects does is that it gives you less energy. It makes it so that you require less energy to pull this one up, to go and you know, become an ion, because it needs like a stable, because it needs, the atom needs a stable outer shell, because this one is far and it really wants to go away. So that's that. And so more shells means further the electrons, further the nucleus. Shielding effect also because when you have more content in the middle, so as you have more protons, you would have more neutrons, and you would have the nuclear contents will increase as you go down, and shielding effect will also increase, which makes the electrons on, like, lower down here, electrons in those shells, in those outer shells, will require less energy to um, pull it out from the atom, because it needs a stable outer shell. Successive ionization energy. So this is actually really similar to the first ionization energy. You would have the same thing occur, but it's not the first electron. It's successive. It's continuing. No, it's the next electron, next electron, next electron, and then it goes on and on and on. So energy until the last 2 electrons. So the definition of successive ionization energy is the energy required to move 1 mole of electrons from 1 mole of gaseous unipolar cations. So when you have a cations, you have that, and then you would go into 2 plus, 3 plus, and then you would see the successive ionization energy. So, but before I'll show you the diagrams on it and explanations, we need to understand the electron configuration one more time, in case we forgot about it. So let's look at that. So the electron configuration for vanadium. Sorry for the notification, I'm really bad at this. And we know that the number of protons is 23 for vanadium, and for the full electron configuration, we need to understand the Aufbau principle. So I'll just write Aufbau right there. So this is the way I'm writing it. You read it diagonally like this. If you draw this in exam, it will help you a lot, because you might mix some sub-levels up. So we know that there's 4 sub-levels, and you have S. S can fit 2 electrons, and you have P, you can fit 6 electrons, and you have D, can fit 10 electrons. You have F, but we don't need it for vanadium, so we'll not, essentially it's the same. You don't have to go over that. It's pretty straightforward. So to start off, we got 1s2, 2s2. We're gonna go on 2p6, yep, and 3s2, right? Yeah, and 3p, yeah, sorry, 3p6 and 4s2, only 2 electrons right there, and lastly it's the D sublevel, 3d3. So as you can see on all of those numbers, it all adds up to 23, and we're good. So that's the full configuration. Let's say we have um, a positive ion, vanadium plus. That means similar thing, 1s2, 2s2, 2p6, no big deal, 3s2, and 3p6. But here's the trick, transitional elements, 4s, it always loses electrons on the biggest energy level, so the 4. So it has 4s1, 3d3, and yeah, that's the positive ion, and you keep on reducing that again and again, 4s to 3d and 3p, 3s if the oxidation state increases. But we also have another method on writing it. So because chemists are lazy and they could just write it as you would have the noble gas before, so argon in this case, because argon has 18 electrons, and you can skip all those time-consuming sub-level writings, and then you can just go straight to the after 18 electrons. So better to see here, it's 4s2 and 3d3, and that's all. Simple. Alright, so this is pick two graphs, this and this. My apologies, because I couldn't find a proper full vanadium successive ionization energy, but essentially it's the same across the one that I got here for potassium, because it's decrease in electrons, removing of electrons. So we know that number of electrons for vanadium is 23. It's the number of protons. This is the number of protons, but protons equals neutron and electrons. So this is the ionization energy. This is the oxidation state form. So basically, how many electrons are were moved, number of electrons. So the first one is about this much, and it's 23 to 22, 20 to 21, 21 to 20, 20 to 19, 19 to 18. Now at this point, now all these electrons are moved, but at this point it becomes 18. Now we know that electrons, when you have 18 electrons, it's on the noble gases. Noble gases are so stable. Sorry. I think it's fine now. Alright, so noble gases are so stable that it requires a lot of energy to remove one electron. Hence, the big jump in the ionization energy. It's a lot of energy, and the big jump. And then after that, it still gradually increases. This second diagram, let's ignore that this is potassium. It's the same thing, but this one use log because of better numbers, because it's bigger energy numbers, so it's easier to write as log as ionization energy. So this is the big jump before that that we found here. Now, and then as you move to 17, 18, 19, 20, 21, sorry, 18, 17, 16, 15, 14, 13, 12, 11, and then as you go to here, 10, it goes to neon, and then it's another jump, 2 jumps. So it's another jump because it's on the noble gas. And one more thing that makes it increasingly that makes the ionization energy increase, this expansion energy, is because that as you go down on the just like what I said here on the on this diagram right here, as you go down and down right here, the energy, no, the nuclear attraction is greater. So you know, when let's say that you really love your bag, and then someone wants to rob it from you, and then you're really strong, and then you have to pull it, and then you know you need that robber, that burglar needs to put a lot of energy to pull that bag from you, right? Because you love that bag, the attraction is greater. And so that's an analogy for this. And then it's sort of it increases again because you need to remove electrons from increasingly positive ions. Like this is like what, 1 2 3, let me see, 1 2 3 4 5 5 6 7 8 9 10 11 12. That's already like plus 12. And I might miscount that, but that's essentially it's the same. And yeah, and then you would go again and again and again, and then it becomes closer to the nuclear contents. Sorry, it becomes closer to the nucleus, and then these big jumps, also another one right there, these big jumps are the jump in shells, the change in them in the big shells. And right about here you reach about helium, and then you need more, so you need more energy to pull those electrons off. So this is the type of questions that you'll get for the E equals HV. We've got questions. We've got 650 kilojoules per mole equals to the HV, Planck's constant and frequency. We know that that is the formula, E equals HV. We have to find the frequency. So that energy, we know that Planck's constant is there in the data booklet. So 6.63 times 10 to the power minus 34. Sorry for the notification. Times V, frequency. Don't forget the units, joules. And as you can see, it's not similar. It's joules and that's in kg moles, so we gotta change it. Now, 650 kilojoules per mole times the Avogadro's constant to get rid of that pesky mole. And we got 650 kilojoules. And moles cancel out, so kilojoules to joules is times 1,000, so times the energy by 1,000, and you'll get the energy in joules, 650, 100,000 joules. Now we've got that out of the way, we have to write it as the 650,000 joules equals to the Planck's constant times joule in joules seconds times frequency. Now we have to find the frequency, so we take the energy in joules, and then you divide it by the Planck's constant. Sorry, that's 35 joules. So, and the units cancel out, and we get 9.804 times 10 to the power of 38 seconds. Now this is another example. Find the limit of convergence of vanadium. It's measured at 185 nanometers. and we have to find the energy, first ionization energy in kilojoules per mole. So we know that the formula is equals HV. I'll write it up here. And there's also another formula we have to use. Speed of light equals to the lambda, the wavelength, times the frequency. And this is the harder part, so hard a bit, but not really. So we got the wavelength, but we have to put it in meters. So there's 1 million nanometers in meters. So 185 nanometers divided by 10 to the power of 9. Easier put, and we get 1.85 times 10 to the power of minus 7 meters. So really small number. So speed of light equals to the meters that we got times the frequency. Now, we know that the speed of light is in the data booklet, right there. So 3.00 times 10 to the power of 8 equals to 1.85 times 10 to the power of minus 7. That's the lambda times frequency equals that. But with simple rearranging, we will find out the frequency. So frequency equals to the speed of light divided by the wavelength, lambda, the upside down y. And also don't forget the units. It's in speed of light in meters per second, and the lambda, the wavelength, is in meters. Units cancel out, and we get the frequency is about, give me one moment, calculation. Yeah, 1.623 times 10 to the power of 15. Now we know that the frequency, these are the common thing that we have from both the formulas. So we write it again as energy equals to Planck's constant times the frequency that we got, so 1.623 times 10 to the power of 15. And we know that the Planck's constant again in the data booklet, right there, that's in joules seconds. Don't forget seconds. Energy equals to 6.63 times 10 to the power minus 34 times 1.623 times 10 to the power 15. Again, if you cancel out the units, it's easier to understand what happens to them afterwards. So writing it all again, energy equals to Planck's constant times the 1.623, the frequency that we got. Sorry for the notification. And units cancel out, and we get energy in joules. Now, this seems familiar, right? Right, so 1.075 times 10 to the power minus 18 joules. But we need it in the answer we need is in kilojoules per mole. So we have to change it. So 1.075 joules times 6 times the Avogadro's constant to add the mole at our answer. Oh, sorry, I forgot the times 10. My bad. That's minus 18. So now we get 647,231.35 joules per mole. Yeah. And that's in joules, and we need it in kilojoules. Basic dividing. Take the answer we got just now, joules per mole, and divide it by 1,000. And we know that joules to kilojoules is divided by 1,000. So we get 647.23 kilojoules per mole. Sorry for the notification. And this is the answer.